my talk. My name is Joon. I'm a PhD student in Professor Wang's lab at Hopkins. Today, I would like to talk about digital ligation-enabled fluorescence-coding PCR for high-dimensional multiplex nucleic acid detection. PCR is the most commonly used method for nucleic acid amplification testing, just like COVID testing, and the use of fluorescent probe, such as TaqMan probe, shown here, is the most widely used method for signal generation. The traditional fluorescence probe-based PCR is one color, one target detection scheme, and the multiplex capability is limited due to the spectral overlaps between different fluorophores. So usually 3 to 4 colors and rarely up to 6 colors are used in the PCR reaction, which means that the multiplexing is usually limited to 3 to 4 steps or rarely up to 6 steps. So there has been many different strategies to enhance the multiplex capability of this PCR reaction. And one of the strategies tries to detect multiple targets within the same fluorescence color by modulating the endpoint fluorescence signal. So as you can see this plot, they try to fine-tune the probe concentration to achieve distinct endpoint signal intensity within the same channel from single targets and also from coexisting targets. And they were able to achieve higher number of plex by simply extending the number of colors. And this strategy was further applied in the droplet digital technology, where each target molecule can be isolated in tiny droplets. So any signal from each droplet comes from the single target molecule. And by tuning the probe concentration in same colors, or by tuning the concentration ratio between 2 colors fluorescence probe, they were able to simultaneously detect multiple targets by using only 2 colors. So this strategy can significantly enhance the multiplex capability of PCR reaction. However, all of this reaction requires multiple primer and TaqMan probe sequences, which can increase the risk of non-specific exponential amplification and also can increase the reaction cost. So to address this issue, here I would like to introduce the concept of fluorescence-coding PCR. If there is a PCR template that has primer and TaqMan probe binding site, then this template can be exponentially amplified by PCR reaction, and the signal can be generated during each PCR cycle. And if you imagine different types of PCR templates like this, which share the same primer and TaqMan probe binding sequences, but the number of probe binding sites are different. In these cases, we can still use the same primer and TaqMan probe sequence to amplify those templates and generate the fluorescence signal. But depending on the number of red or green probe binding sites, different endpoint signal will be generated. And those endpoint signals can be transformed into the geometric space in this 3-dimensional form. So to apply this fluorescence-coding PCR concept for multiplex target detection, we have developed ligation-enabled fluorescence-coding PCR, or dLiNC PCR. So in this assay, here we have a ligation pair that has target complementary region, a universal primer, and TaqMan probe binding site. So in the presence of target sequence, this ligation pair will be ligated, and this ligation product can be further used as a fluorescence-coding PCR template. So using this strategy, we have designed 10 ligation pairs that share the same primer and TaqMan probe binding sequences, but the number of red and green probe binding sites, as well as the target complementary region, are different. So in this dLiNC PCR assay, we have a mixture of 10 ligation pairs, and in the presence of each target, corresponding ligation pair will be ligated in the first ligation reaction, which will be And the ligation product can be further used as a template in subsequent fluorescence-coding PCR, which is just standard PCR using only one pair of primary and secondary. And of course, the endpoint fluorescence intensity can be transformed into this plot and target can be identified. So in this paper, we have investigated the design rule of ligation pair and optimized each of the reaction conditions and have experimentally shown that in the presence of each target, distinct red and green fluorescence intensity can be generated. I don't think it's very obvious in this presentation, but different red and green endpoint intensity were generated, and each target can be identified using this two-dimensional plot. And since the dLiNC PCR utilizes bulk-based TaqMan PCR, coexisting targets cannot be identified because the endpoint fluorescence intensity will be all mixed up, which means that this dLiNC PCR is limited to identify only one target at a time. So in order to overcome this limitation, we employ the digital PCR technology and named it as digital dLiNC PCR. So in this digital dLiNC PCR reaction, coexisting targets can generate multiple ligation products in first ligation reaction, and each of the ligation product strands can be isolated and partitioned into tiny digital wells in subsequent digital fluorescence-coding PCR. For the digital PCR, we use commercialized QuantStudio digital chip that contains 20,000 microwells, each with 0.7 nanoliter of reaction volume. So after the digital fluorescence-coding PCR, the endpoint fluorescence intensity in each microwell can be measured by fluorescence microscopy. And the endpoint signal from each microwell can be a single data point. So there will be 20,000 data points generated after the digital PCR reaction. So in this digital dLiNC PCR, coexisting targets can be identified simultaneously, and also target quantification can be achieved by counting the number of microwells that generates the pre-designed fluorescence coding signal. For target quantification, we use statistical approach. In statistics, confidence region is defined as a multi-dimensional generalization of confidence interval with a certain degree of confidence level. So in the case of digital dLiNC PCR with two colors, a variant distribution can be obtained where X and Y axis are green and red fluorescence intensity and Z axis is frequency. So using this bivariate distribution, confidence region, also known as confidence ellipse because of this elliptical shape, can be generated. And the area of confidence ellipse depends on the confidence level. So using this concept, we have generated 10 confidence ellipses with a 90% confidence level from 10 independent experiments and define them as target detection regions. So we can count the number of data points within each target detection region for target identification and quantification. So using those 10 target detection regions, we performed 10-plex two-color digital dLiNC PCR for simultaneous detection of 10 DNA targets. As you can see, these plots, the number of data points within each detection region decreases as a function of decreasing target concentration, and there were no data points within any of the detection regions in the absence of target. We further varied each of the target concentration from 100 all the way down to 1 attomolar and observed linear relationship between percent positive and target concentration. And we also calculated ID efficiency of each target detection region, as shown here, and observed consistent ID efficiency across different target concentrations. In summary, we have developed digital ligation-enabled fluorescence-coding PCR, or digital LINC PCR, that can simultaneously detect multiple DNA targets, not only DNA, but any kinds of nucleic acid target in a single reaction. And this digital LINC PCR is a simple two-step reaction, which consists of multiplex ligation and subsequent digital fluorescence coding PCR using only one pair of primer and code. By designing the ligation pairs that has target complementary region, universal primer binding site, and varying numbers of red and green technical binding sites, we were able to simultaneously detect 10 DNA targets by using only 2 fluorescence colors. The multiplexing capability of this digital LINC PCR is further enhanced by modulating the number of red and green technical binding sites. It's very easy, and also it can be achieved by adding additional fluorescence colors. I would like to thank my advisor, Professor Wang, and I also want to thank Dr. Chen for his collaboration on this work.